I have a cooling tower. Actually, this is just a part of cooling tower with very like small part of cooling tower. And I have water go in. This is water. Water go out. This is liquid water. And then we have air, which is gas. This equals to you have water gas plus like air gas, and we have air going out. This is vapor water, and so I have Y is vapor water over the total air. So I have we have the liquid, like the liquid water go in. Mass flow rate of water go in is 50 kilogram per second. This is like per 1 meter squared because we have area is 100 meters squared. Temperature of water is 7 degrees Celsius. Temperature of air going out, so like TA out is 40 degrees Celsius, and we have 90% relative humidity. From here, so from here we have so we have the liquid water, like the mass flow rate of liquid water is 0.5 kilogram per meter squared per second. This. Then we have the total. This is we have A is the total. Actually this is like the total interaction area of water and air. This equals to A is A times A times the we have the inside we have like small a, no, not small a, but like the cross section is 5 meters squared per meter cube. So we have to multiply by this. So I said this like small a, yeah, whatever. So the small, like the total interaction area of water and air, contact area, equals to times A. This would be 100 meter squared times 10 meter times and we have Z, like the height, like we have Z equals to 10 meter, so we have to multiply it by Z as well to, like, this is the contact area of water and air inside of the cooling tower. We have to multiply it by the total volume, so we multiply it by 10, and A is like 5 meters squared per meter cube, which give us 5,000 balance for water flow, which is we have the mass flow rate of water multiplied by heat capacity of water, and the heat capacity will relate to the temperature change of water. But here we have to multiply it to the area to to know how much water go through the a cross section area. So we have this will equals to our heat flux. We also have this is the total area that water will go through. We multiply it to the molar flux of water, so we have Kc times concentration of water divided by concentration of water, like in a bunk concentration of water. And this is the energy balance. So, but like this one is only like the mass. This is only like the mass balance. So this, well, we have to. This is the molar flux. So we have to add the temperature change to see like how much, because this has, because energy balance will relate to the energy, like the heat change of water and air. So we have to have the heat capacity of actually this is like the not heat capacity, the heat coefficient of and then multiply by the difference between the heat of water and air and water. So I will have to see like the units. This is kilogram per meter squared per second. Area is meters squared. This would be joules per kilogram times Kelvin, and this is Kelvin. This, in the left hand side, the unit of the left hand side would be joule per second. In the right hand side, it would be this is meter squared. Like all of this would be meter squared. This, the units of molar flux is mole per meter squared per second. And unit of this H is joule per second per meter squared per Kelvin, and this is Kelvin. So as we can see, like in this, we cannot add these two together because it's the differences of the unit difference. So we have to from here we know that this is cross it. We have joule per second per meter squared, but like in here we have to. So in here we have to multiply something, like we have to add like joule per mole. So from here we can end up with the joule per meter squared per second. So the unit of this would be like something lambda is what we call it is the heat of vaporization of water. So, and we end up with this, and then we multiply it by meter squared, so we will have joule per second. Next is the side, the side like plus or minus of this, like this H and this. Lambda times Kc. We know that temperature of air is higher than temperature of water, so this is like positive. This is positive, and this is also positive, so H should be positive. But from here, we know that in the left hand side is positive number, but this, like this one, would be negative, because we know that the concentration of water at bunk temp, like the bunk concentration of water will always like higher than the concentration of water in the interface, so it will be negative. But this is positive, so we have to have the negative side to make it positive. So from here, we know that we have the differential equations of temperature, of water temperature will be this is the mass flow rate times area, cross section area, times concentration, heat capacitor of water, times the temperature. It will be A times A dz times negative lambda Kc times concentration of water at the interface minus concentration of water at a bunk area plus H times the temperature of water minus air minus temperature of water. For water, for the steam, like, or air. Similar to that, we also have I said the constant, like the mass flow rate of the vapor water times area times heat capacitor of air times dt of air. This equals to area, like the total contact area times area times dz, like times the volume. Is this the same thing of C of air at the interface minus air at the bunk area plus H, also like plus H of TA minus T air minus water. But we don't have this, the mass flow rate of water, of the air, including the vapor water. So, but what we have is we have G equals to G air plus G water, and we also know that G air equals to pressure times m, like the average molar mass over RT. All right, and we also have the molar mass average equals to GA plus G water over GA's over MA plus G water, like the mass flow rate of water over mass concentrate molar mass of water. This is one. Equation 2. We also have the mass of water, the mass flow rate of water over concentration, molar mass of water equals to Y. We know Y is like related to the humidity, the relative humidity up here. So we have here we will have Y times G over MA average. So from 1, 2, and 3, we will have the mass flow rate of air in. So we have the differential equations of the temperature of the air temperature of the steam. So we have G times A times CPA ETA equals to, like, this would be the negative Kc of CAI minus CA bunk plus H over TA minus TW. Okay, so this is the area, like the differential equation of the steam. So from here we will know the differential equation for, we can derive the differential equation of the air temperature like this. The third part is we have to derive the differential equation of the fraction of the water fraction. So we will use the mass balance to find it. We know that we have G times dy, actually G over M average times dy. This would be fraction, the mole flow rate, yeah, of water vapor in the steam. But we have to multiply it by the area, so we will see like how much the vapor water will go through the specific area. We also have, in the right hand side, we also have this part, but this time we only need the mass balance, so we only need the molar flux. So this is Kc times, we only need this part. With this, like, will be the pressure, the vapor pressure at the temperature over RT, and this will be the pressure Y times Y, like times Y of the, and then over RT. So we know everything. We can derive the fraction, the water fraction. But we can see here, like, we know H here, but we don't know Kc. But it like appears on all of 3 equations. To find Kc, it will relate to the Nusselt and like the Lewis, and like it will relate to these 3 numbers. We have Nusselt number equals to 0.6 Reynolds number over 1 to the power of 1/2, and Pareto number 1/3. So from here, we have Smith number equals to 0.6 times Reynolds number over 1/2 times C over 1/3, and we have the Lewis number is this. All right. So we have this equals around 1. So because we can see like this Lewis number is like this number over the Nusselt number. So we have SH over NU equals to, we have KC times D over driving force of AB. Nusselt number equals to the H times also times D over K. This equals to, because we can see like this over this, so we have this, we can cross this, and then it equals to SC over PR to the 1/3. So from here, this equals to the Lewis number to the 1/3, and this fraction, this equals to what is that? Actually, we can cancel this, so we can have KC time over H times K over DAB equals to the Lewis 1/3. All right, and this will equals to actually, like, I will just go from here, like the Lewis number equals to Smith number over Prandtl number. This equals to, doesn't make mil, no, rho DAB. Prandtl number equals to mil over rho K, like thermal conductivity, times rho CP. Okay. So from here, the Lewis number equals to, and cross this, and then the Lewis number equals to K over rho DAB times CP, like that. Okay, so from here we can put it back up here. So we know that K over DAB is this part, so we will have so from here we have KC over KC small c over H equals to this part will equals to times Lewis number times rho times CP equals to Lewis number over 1/3. So because the Lewis number is 1, so we can just cross it out, and this will be 1. So we have KC equals to H over rho CP. We know H, we know rho, we know CP, so we will know the KC, and we can put KC to like these 3 equations. Like we put KC into this, and also KC into this.